Hello, this is Dr. Viv. In this video, we shall solve a problem where there's friction between the upper block and the lower block, and let's assume that the static and kinetic frictions are given and they are not zero. But there is no friction between the lower block and the floor. The lower block is being pulled and the upper one is being pulled along by the friction mu. So the problem involves two different kinds of pulling forces. For a slow pull, which means small value of Fp, find the accelerations of the blocks. So you can expect that for a slow pull, both the blocks will move together with a common acceleration. For fast pull, find the accelerations of the blocks. So if you're familiar with the party trick of pulling a tablecloth from under a wine bottle, so if you pull it out really fast, the wine bottle will more or less remain where it is on the table. So that is what you can expect. You can expect that the lower block will move while the upper block will move less. So the accelerations are going to be different. And then what's the minimum value of the force that will cause the accelerations to be different? That's a critical value. So let's solve this problem. The starting point is always to draw the free body diagrams. So we'll go with that. I'll draw the free body diagram of the upper block first. You're going to have a number of forces. The normal force from the lower block, which I'll indicate by Fn 2 on 1. The force of static friction, this is for the slow pull. For the slow pull, there's going to be no relative motion, so there's going to be a force of static friction acting 2 to 1. The weight, which I'll draw as big as the normal force, and that is m1g. And those are all the forces that act, producing an acceleration to the right, which I'll call A. For the lower block, the free body diagram looks like this. First of all, there's going to be the reaction forces, so equal and opposite. So the reaction force for the force of friction is going to be the force of friction static 1 on 2, and then the reaction force for the normal force is going to be the force of normal 1 on 2. Observe that the weight of mass m1 is not acting. It's a normal force that acts. So the weight is coming through the normal force. Separately, the mass m2 also has gravity acting. So we have m2 times g. And then you have the normal force from the floor, which I'll simply call F sub n. And then there's the pulling force, which is F sub p. So there are 5 forces acting on the lower block, M2. Once we have all these forces, the next step is to create the force table. Let's do that next. The force of friction acts in the positive x direction. The normal force acts in the positive y direction, and gravity in the negative y direction for block 1. For block 2, we'll have the normal force from the floor, the reaction force of friction Then the pulling force, x component is cosine because adjacent side, y component is sine because of the opposite side, and both components are positive. Then there's the weight. Let's see, there should be one more force, and that is the normal force. So there's 0, negative Fn 1 to 2. So those are the 5 forces for the second block. Now we have to, as best as we can, solve these. So let's use on the first force table Newton's second law, which says that sum of all the forces is equal to mass times acceleration. So the sum of all the forces in the y direction equals 0 because there is no upward flight. So that gives me Fn 2 on 1 is equal to m1g. Then I have sum of all the forces in the x direction equals m1a, and that gives me the force of friction static 2 on 1 equals ma. Nothing more can be done, so we'll move on to this side. The sum of all the forces in the y direction is going to be a complicated mess, and it'll involve the reaction force of the ground, which I'm not really interested in, so I'll focus on the x direction here, is equal to m2a. Well, that gives me the sum of those two forces, negative ff s 1 on 2 plus fp cosine theta is equal to m2a. Now, by Newton's third law, the magnitude of ffs21 is equal to the magnitude of ffs12. So I'm just going to replace that there. So I'm going to get negative m1a plus fp cosine theta equals m2a. Now at this point, what I'm going to do is simply add m1a to both sides. And when I do that, I get fp cosine theta equals m1 plus m2 times a. And then divide both sides by m1 plus m2. That gives me the acceleration. Now this result you need not have struggled so much to get. You can use the lump philosophy. Since they're moving as a lump, the acceleration is obviously going to be the x component of the pulling force divided by the total mass. So that really makes sense from that point of view, from the lump philosophy. So I'll write it makes sense from the lump philosophy. Okay, now let's try the second. That's the first part of the problem. The second part of the problem is what happens when the pull is not slow. What if it's fast? For fast pull, the only thing you would need to do is remember that there's going to be now relative motion between this and this, so you only have to change the static to kinetic, and then the accelerations are going to be different. Instead of the same acceleration for both of them, you're now going to have A1 for this and A2 for this. So let's make a note of the changes. I'm not going to bother drawing two separate free body diagrams and two separate force tables. You should try doing that on your own. But I'll just note the changes here. For fast pull, the two things we're going to do is change static to kinetic. And then separate accelerations. Let's look at the free body diagrams for these two things, pretending that I've done those changes. So in other words, I've written K here instead of S, and I've put A1 here and A2. That's about it, no other changes. So M1, This equation remains. The first equation remains the same in the y direction. So I'm going to write Fn 2 to 1 is equal to m1g. And then the force of friction kinetic 2 to 1. I had force of friction static 2 to 1 equals m1a. Now I'm going to write force of friction kinetic 2 to 1 equals m1a1. We also have the law of friction. The law of kinetic friction says the force of friction kinetic 2 to 1 equals mu kinetic times the normal force 2 to 1. I'm going to substitute for FFK21 from here, and for normal force I'm going to substitute m1g from there. Observe the mass cancels out, and the acceleration a1 is just mu kinetic times g. That's an important result. We have found the acceleration of the top block. What about the acceleration of the lower block? There, we go back to this equation that we wrote here, except we make the suitable replacements. So I'm going to get negative f sub f k 1 to 2 instead of s, I write k, plus fp cosine theta is equal to m2 times a, but m2 times a2 this time because it's two different accelerations. I divide it by m2 next, so I get a2 then. For FFK 1, 2, I'm going to use Newton's third law. FFK 1, 2 in magnitude is the same as FFK 2, 1, and FFK 2, 1 is just mu kinetic times mg. That's FFK 2, 1 is mu kinetic times mg over there. So I'll just write all that. It's going to be negative mu kinetic m1g plus fp cosine theta divided by m2. So that's the second acceleration. The two separate accelerations have been found. Now the third question can actually be answered from the very expressions that we've already obtained. So the third question says, what is the minimum value of fp to cause accelerations to be different? So what we're going to do is, for that, all we would need to do is the acceleration a2 would have to be bigger than or equal to the acceleration a1 for relative motion. But because motion has not started yet, you will replace in all these formulas mu k by mu s. So this is fairly subtle stuff. Since we have not, the accelerations are same initially, and then at some critical value they become different. So we have at that critical value we get by putting mu k equals mu s, and after that, after they separate, you can go back and put mu k for both of them. So the critical condition is given by a2 is negative mu s m1g plus fp cosine theta divided by m2 is greater than or equal to mu s times g. So I've just made the replacements of mu k with mu s in accordance with what I discussed about to move. All right, let us solve this. Multiply both sides by m2. And then add mu s m1g to both sides and divide by cosine theta. So I get the critical value, fp critical, is bigger than or equal to mu s m1 plus m2 times g divided by cosine theta. And once you're past this critical value, you can immediately lower the force to be mu sub k m1 plus m2 g over cosine theta, and they'll still move separately.